Hey friends, this is Mrs. Gregerson, and we are working on our lesson 1-1, talking about logical reasoning. And logical reasoning is just the way that we think. I mean, we all think that way, and in math we have to learn to understand which thinking process we're using and be able to identify it well. Well, the first type of thinking that we do is deductive reasoning, and deductive reasoning is reasoning based off rules and facts. Now, understand, we all are really that way. That's how kind of life functions a little bit. Let me pull this in a little, my friends. And that's like math itself. We know 1 plus 1 equals 2 because we know the rule of adding 1 to a number gets 1 more to a number. We also know, like, you're tardy for a teacher's class based on that teacher's rules and standards. You have late work policies, anything like that, that's a rule we follow. Like, if you're going over 10 miles per hour over the speed limit and a police officer pulls you over, there's a good possibility you're going to get a ticket because that's the rule. So it's kind of the reasoning that we use for that. But here's some just some fun examples of doing this. Like, every year you get on your birthday, you get 1 year older. Yeah, we all know 365 and what is it, a quarter days, the half days, whatever, something like that. Days that you have make you a year older. We also know a number multiplied by 1 is equal to itself. Hey, we all know the multiplication identity property. It says if I multiply, like 5 times 1, I know it equals 5. 1's that wonderful identity number. And then we had any mathematical rules like multiplication, subtraction, division, Pythagorean theorem, any of that type of stuff is going to be used with deductive reasoning. So when you do this, this is always rules based. There's always a standard based with this one. Then we have intuitive reasoning. Now this is kind of the fun reasoning. This is reasoning based off of feelings. So this is when I say people get their emotions involved. Feelings and gut instinct. There's not always logic behind this at all. Basically most of the time it isn't. Like, just a quick easy example of this is like when a baby is crying, it's hungry. A newborn does not sit through this process and goes, well, today I'm going to think about the fact that babies have to cry in order to get fed. No, a newborn comes out and it screams, it wants food. That's the type of process, that it's instinctive. Animals are instinctive. Some of you kind of take deductive reasoning and you turn it into intuitive reasoning. For instance, those of you in athletics, let's just say your job is to be able to shoot a basket without even thinking. It's just like perfect every time. Well, what do? You shoot it over and over again to the point where you don't even think about it anymore. It's now turned into an instinct. Your moms are absolutely amazing at this with mothers' intuition. Like, you walk in the door, your mom hasn't even looked at you, and she goes, honey, what's wrong? You've had a bad day? And you're like, how do you know? No one's talked to you. How did you get, this process? And let me tell you, as a mom, we just know, and don't ask me how. And as teachers, we just know, don't ask us how, okay? It's just weird, it's instinct. Another example of this is maybe like you're driving home, and for some reason you decide to take the long route home instead of the shortcut route home, the shortest distance, and you find out later there was a car accident. You just don't know why you did it, you just did it. Well, maybe it was the Lord, helping you be safe, but that's more of the instinctive. We might call that conscience, or the Holy Spirit. The outside world would call it, instinct or good luck. Another one is, today is what we're really going to be focusing on, is inductive reasoning. And inductive reasoning is is the most natural reasoning that we do as a kid or as an adult. We just look around and we observe. Inductive reasoning is reasoning that is based on observing patterns. So we observe patterns. Now understand, that means you're looking, you're watching, you're taking information in. Like when I look in a classroom, I look to see, I can tell if it's cold outside by looking what you guys wear. Oh, a majority of them are wearing sweatshirt and jeans. It must be cold outside. That's inductive reasoning. Science are very good at this. Inductive reasoning is how they come up with their hypotheses and theories to test, is they watch to see what's out in the real world. Let's see if it actually physically happens every single time. They test it. That's inductive reasoning. IQ test, huge that people do them. It's based off of inductive reasoning most of the time. Who are really good at inductive reasoning? Oh, detectives are really good at doing that. Lawyers are really good at seeing where this stuff comes in by observing detail. Teachers see that, like, you know, there's that student who's always turns in their homework a day late. Well, that's inductive reasoning. That's a pattern that's developed. I will probably start automatically assuming it is going to be late. You know, that type of rules. But here's just a simple, easy pattern that you have done before in your past, like a number pattern. 7, 14, 21, 28. And yeah, we know we just add 7 more and you get 35. It's the next multiple of 7. Pretty simple. Another one be a visitor at WA observed. Noticed is another word. Noticed. Looked that some students ate in the commons during lunch and some students ate outside during lunch. He conjectured that students at WA can choose where they eat lunch. Well, yeah, you do. That's unusual in a lot of schools, so a person on the outside would see this. Or how about cell phone usage? People, when they come to shadow, and many of you did, you look to see if this was the right fit for you, or you were observing the teachers, you were observing the students, you were observing how things interacted. Some other examples of this is looking for like patterns with symbols. So like here I'd have a triangle and I have this arrow going up, but now that arrow is going to the side. Here's the same triangle, now I'm going to this side. I mean, what would be your next one? Well, obviously, we'd probably think that this wouldn't be going up. Now someone goes, how do you know for sure it's going to keep going inside? That's when I probably should have shown you about 5 or 6 of these. And then you'd be like, oh yeah, for sure, I'm going counterclockwise around the triangle. Here's another example. I have a circle. I put 1 slash in. I have another circle. And I put 2 in. Actually, yeah, let's do it this way. I realized I forgot to put my first circle down. And the first circle, so this would be number 1, number 2, number 3. So sorry about that. So circle, slash, dash. Now, I'd ask you in class, what's next? And I guarantee you I'll get 2 different probably examples most of the time. The other day in class it was fun, I got 3. Okay, someone said it could be an open circle. Well, okay, based off of what you see, I don't think so, but that's a logical observation. Like maybe they're going to repeat the pattern. Another valid one that I think would be an observation with this is that I'm putting 3 together. And I keep dividing it. And so I do it in 6 equal parts. So you just keep adding 1 line and evenly using it. Line segment, evenly dividing the circle up. Or you maybe had this one, and this is actually one I was thinking about. I kept saying you doubled the divisions. So if I go from 4, I'd go to 8. So for me, I thought this would be the division. But to be honest, as long as you observe the pattern, you make that assumption based off of it. We can assume wrong, but we still make that assumption. That assumption we call is a conjecture. A conjecture is a statement based off inductive reasoning. What does it mean? I look for the pattern and then I make a statement about it. In science, we would call that the hypothesis. That's your assumption that you made. And we normally say don't assume, but inductive reasoning, that's the process of thinking when you do that. So that's how it kind of works. So it's the process based off of inductive reasoning. So it's a statement. Little kids do this. My 5-year-old has decided that heaven has to be on a cloud. Well, her thought process is heaven's not on earth, so it must be on a cloud. We've had the weirdest conversations lately about theological things, but that's her inductive reasoning. That's her way of reasoning it through. She goes, well, if it's not on earth, like right next to me, then it has to be up in the sky. You know, and for her, that's a valid reason process. But as you know as well as I know, an observation could be wrong. You know, I could observe that person's depressed, but maybe their personality is they just don't smile. You know, we could still have wrong statements. Now here is an example of a conjecture that many of you know. It says the sum of 2 positive numbers is always blank. Well, if you think about it, you can easily come up, you know, you can go 3.5 plus 7. Oh, that's 10.5. We always know because of the number line that it's always a positive number. And we could prove, not really prove it, but sure much get a good idea that would be the case by just working out and seeing a pattern that's actually growing based off of this. So it'd be pretty cool. Now, here's the thing you need to understand. To know if a conjecture is always true, you must prove it. It has to be right at all times. Okay? Like this top one, that's just a basic algebraic rule that we all know when we work with integers. A positive plus a positive is always a positive. But we could also be wrong. See, a conjecture can be false. And if it's false, you have to find this one little example that makes it not true. So if you find only one example that makes the conjecture not true, you call that a counterexample. Lawyers are phenomenal on this. They use counter arguments all the time in court. They sit there and say, yeah, I'm countering this argument, and they prove something didn't work in a case because they can show that this was a possibility or this actually happened. To me, that's a phenomenal skill. A counterexample, it can be a diagram, which is huge, you know, in geometry world. A statement, maybe a rule that proves it otherwise, or a number. You have a lot of different possibilities. So here's a few things you remember. You have 3 types of reasoning. You have deductive, rules of facts; intuitive, based off your kind of gut instincts and just knowing, be able to do. Then you have your inductive, which is based off of observing patterns, and then we make natural conclusions based off of those patterns, which are called conjectures. Are you guys with me so far? So let's look at this next one right here. So show that the conjecture is false by finding a counterexample. Well, with this one, we say for every integer n cubed is positive. Well, a lot of you are like, oh, we instantly can see the error there. Because obviously when I go 1 cubed, it's definitely positive. But what if I put a -1 in? Well, -1 times -1 is +1, times a -1 makes it a -1. There is your counterexample. That's the process. We can just prove it by giving that one example. All right, now we have to also decide if conjectures are true and false. And if they're true, we can't disprove it. But if it's false, we can totally disprove it. So like the first one, the quotient of 2 negative numbers is a positive number. Now let's go back to algebra mode. You probably should realize if I said quotient, that means division, right? So the quotient of 2 negative numbers is always positive. Well, -3 divided by -4, is that a positive? 3/4. Exactly. So this is a true statement. We know, again, with integers, we learned this before. Here's another one. It says every prime number is odd. Now remember, a prime number is any number that's only divisible by itself and 1. That's actually a false statement. And the reason why is because of what the first prime number is. The first prime number is 2. It's even. It's the only even prime number. Kind of cool, isn't it? It's the only even prime number. So here is an SAT, ACT hint, okay? When you work with the SAT or ACT, they will ask you to add the sum of the first 5 like prime numbers, or multiply the first 3 prime numbers. They on purpose know that most people, if they're going to forget a prime number, it's the number 2. So therefore, they will put in the wrong answers for those. That's happened to me, and I used to teach a class before. So know that they will ask you a prime number problem, and you can't forget the number 2. It makes a huge difference. And then we have 2 supplementary angles are not congruent. Remember, supplementary angles are 2 angles that add up to 180. And we know this is false because we know 90 degrees plus 90 degrees equals 180. Well, those are congruent. They're the same size of angles. So we know it's false. But how about the next one? The square of an odd integer is odd. Now, some of you are like, I don't know. We'll start playing with the numbers and see if there's a pattern being developed. I have 1 squared equals 1. We have 3 squared equals 9. We have 5 squared. Oh, that's 25. We have 7 squared. That's 49. Now think about this for a moment. If I keep going, will I always have an odd number when I square an odd? And the statement is, it's true. Now let me explain to you why. In order to be even, you have to be divisible by what number? 2. Well, any of these numbers here, the odd numbers, are they ever divisible by 2? No, they're not divisible 2. There's no factors of 2, so therefore there's no way they could ever be even. So that is a true statement. Now, for homework, you have a couple different things. You guys have to do a worksheet, and all you do is identify the 3 types of reasoning. Be careful. They're very tricky to see sometimes. Very much between deductive and inductive reasoning, be very careful. okay? Second of all, you have the book work, and it's developing patterns. Please write down how you found the pattern and then the answer to the patterns. I think you guys will do a good job. But don't also forget, with inductive reasoning, sometimes it's really good to think outside the box.